so what I have is the following. So, let me call this as 1 and let me call this as 2. So, let me show you the proof of the result 1. So, the result 1 shows the Z transform of f of n minus m. By definition, this is the summation n from 0 to infinity f of n minus m z to the power minus n. I see that if I put r equal to n minus m, if I do this substitution, I see that the Z transform is, so I replace n by r plus m, right. So, I get that this is z to the power minus m summation, this time r. So, r is from n minus m. So, when n is 0, r is minus m, and when n is infinity, r is infinity. So, f of r z to the power minus r. Now, let us now rewrite this integral. In particular my integral, let me just again rewrite. So, this is Z transform of f n minus m. I have shown this equal to z to the power minus m summation r from minus m to infinity f of r z to the power minus r. So, this is also equal to z to the power minus m summation r from 0 to infinity f of r z to the power minus r plus the summation r from minus m to minus 1 f of r z to the power minus r. Okay. So, what I see that is this is also equal to z to the power minus m times, note that this first summation is nothing but the Z transform of small f of the function. So, this is the Z transform of the function plus the summation r from negative m to minus 1 f of r z to the power minus r, and that is my right hand side of the expression 1. Similarly, to show the second result, all I have to do is to use the substitution r equal to n plus m. Basically, whatever is inside the argument of this function, that is the variable that we substitute. Okay. So, let me just quickly show that. So, n from 0 to infinity f of n plus m times z to the power minus n. I see that if I use my substitution r equal to n plus m, I arrive at the following sum. This is summation r from negative m to infinity, well, r from plus m to infinity f of r z to the power minus r, and then when we rewrite this, I get z to the power m times summation r from 0 to infinity f of r z to the power minus r minus the summation r from 0 to m minus 1 f of r z to the power r minus 1. Okay, I see that this is also equal to z to the power m f of r minus summation r from 0 to m minus 1 f of r z to the power r minus 1, and that is the expression that I had on the right hand side of 2. Okay. Moving ahead, let us let us look at some more properties of the Z transform, and then we will solve some examples using this difference, using this translation of the Z transform of the function. Okay. So, let us look at another result. Again I write this result in the form of a theorem. The theorem shows that this is the theorem with relation to the multiplication of the function with a factor. So, if I am given that the Z transform of the function f of n, let us denote it by capital F of z, then I have 3 results to show. I have the fact that Z transform of a to the power n f of n is the Z transform of Z by A, and of course, I need to specify that the Z transform is defined in an appropriate region, and the second result is that the Z transform of e to the power negative n b f of n is Z transform of Z times e to the power b. This is for all values of z greater than e to the power negative b, and the Z transform of n f of n is negative z d d z of f of z. Okay. So, now I am not going to prove all the results, because the first two results are very straightforward. If I look at my example, so recall my example 1, recall example 1, where I found, well, not even recalling example 1, if I were to just use the definition of Z transform, right. So, let us just look at the case 1 quickly. So, the Z transform of a to the power n f of n will be summation a to the power n f of n z to the power minus n. So, n from 0 to infinity, and if I were to rewrite this, this is the summation n from 0 to infinity f of n z of z by a to the power negative n. I see that this is nothing but the Z transform with respect to this new variable z by a. Okay. So, of course, appropriately defined in an appropriate region. And then in the second case, if I use my a to be e to the power negative b, I arrive at my result. So, just use e to the power negative b to be a, and that is, so instead of a I replace e to the power b, and that the second result immediately follows. The third case, let us look at the third case. So, I have to evaluate the Z transform of n times f n. So, let us write down the definition. This is from 0 to infinity n times f of n z to the power minus n. So, if I were to write, let me just slightly process this expression. This is also equal to z summation n from 0 to infinity n times f of n z to the power minus n plus 1. Okay. So, what I get, that this is also equal to z, what I get is the following. So, this is z times the infinite sum n from 0 to infinity f of n times d d z of z to the power n, right. So, z to the power minus n. Okay. So, if I take the derivative, and of course, with a minus sign as well. So, now the next step is that I am going to replace, I am going to take the derivative outside the summation. So, if I do that, what I get is that the Z transform of n times f of n is negative z. I have taken the derivative outside the summation. So, d d z of summation n from 0 to infinity f of n times z to the power negative n. Notice that the argument inside this derivative operator is the Z transform of f. I see that this is also equal to negative z times d d z of the Z transform of f. Okay. So, then let us now generalize this result. So, I am going to generalize my result 3, namely that the Z transform of n to the power k times f n is negative 1 to the power k times this operator, the kth power of this operator z times d d z. So, this operator operating k times on my z transform f of z. So, my k's are my integers, my positive integers, and so I am going to use this general form as and when the need arises. So, then I have one more result, and that is the result with regards to the division of the z transform with a factor. So, let me call this as a division theorem. So, it tells me that the z transform of f of n by n plus m is given to be negative z to the power m integral from 0 to z f of zeta d zeta. So, the result shows that the z transform of this argument is negative z to the power m times the integral of the z transform divided by zeta to the power m plus 1. Okay. So, to come to the proof of, to show the proof of this result, let us start with the left hand side. So, the left hand side says that this is z transform of f n by n plus m. So, this is also equal to the summation n from 0 to infinity the z transform of f n by n plus m times z of minus n. So, that is my z transform of this argument. I see that, let me just rewrite this expression. So, let us look at this particular expression. So, I am going to divide by z to the power m and I am going to multiply by z to the power m. So, what I am saying is the following. So, I get that this is also equal to z to the power m summation n from 0 to infinity f of n divided by n plus m times z to the power minus n plus m. So, why I did that is I am going to rewrite this particular expression, this particular factor z to the power minus n plus m by and represent it by an integral, namely this particular integral. This particular integral is as follows. So, this is integral 0 to z. Let us introduce a dummy variable zeta. So, zeta of negative n plus m plus 1 d zeta and with a negative sign. So, students can check that if I evaluate this integral, I am going to get back this expression z to the power negative n plus m. So, let us replace this expression by this integral to come to this new sum. So, the new sum is negative z to the power m summation n from 0 to infinity f of, well, so this integral is this particular expression. This particular expression is given by this integral. So, I have f of n times the integral 0 to z of zeta to the power n plus m plus 1 d zeta. Okay. So, what I have done is I have replaced this entire expression that I have circled here by this integral. Okay. So, let me just rewrite what I have just written. So, what I have shown so far is the z transform of f of n divided by n plus m is this expression negative z to the power m summation n from 0 to infinity f of n integral 0 to z zeta, well, the function zeta, well this is chi not zeta. So, the function, this variable chi to the power negative n plus m plus 1 d chi, and let me just check if I have missed anything. No. So, everything has been included. So, then the next step is I am going to interchange my sum and my integral. So, I am going to interchange my sum and integral. So, notice that this is also equal to negative z to the power m, and let me just take this integral out, integral 0 to z, and what I have is the sum. Well, so let me also take out this factor, this chi to the power m plus 1. So, chi to the power minus m plus 1 times the summation n from 0 to infinity f of n times the factor chi to the power minus n d chi. Okay. So, we see that this is nothing but the z transform of the function small f. So, rewriting again. So, I get that this is integral 0 to z 1 by zeta to the power m plus 1 times the z transform of the evaluated at the variable zeta, evaluated at the variable chi d chi, and if students can check that this is the right hand side of our result. Okay. So, what I have shown here is that the z transform of this of the function divided by this factor can also be written in terms of this integral of the z transform. Okay. So, then another result that I have is related to the convolution of the z transform. So, I am going to state it in the form of another theorem. So, this is related to the convolution. The convolution, it tells me that if I am given the z transform of two functions, let us denote it by capital F and capital G, this is also equal to the convolution, then the convolution of f star with G is the convolution of f, well, the z transform of f times the z transform of G. Namely, well, I need to define the convolution. So, the convolution of two functions in the z transform sense is defined by this summation. It is defined by summation m from 0 to infinity f of n minus m g m. Okay. So, this is my convolution in the z transform sense, z transform sense. Okay. So, let us look at the proof of this result. So, to look at the proof of this result, let us look at the left hand side. I have that I have to evaluate the z transform. So, let me call this as my result A. So, I am looking at the LHS of A. So, the z transform of the convolution of two functions is by definition n from 0 to infinity z to the power negative n times, well, the convolution, let me write down the convolution, this is summation m from 0 to infinity f of n minus m g of m and then the summation over m. So, then let me then interchange these two summations. So, I am going to take out the m summation out and n summation in. So, let me interchange to come at the following expression. So, the z transform of f convolved with G is the summation m from 0 to infinity. Well, so that will be, let me just take the functions of m completely out of the n summation, and so I am rewriting now. This is the summation over m times the summation over n from 0 to infinity times f of n minus m times z to the power minus n. Okay. So, let us now use the expression, let us now use a new variable defined by r, which is equal to n minus m. So, I get that this is also equal to the summation m from 0 to infinity g of m summation. Note that if n is 0, then r will be from minus m to infinity, and my new variable, with respect to the new variable, the interior sum is f of r z to the power minus r plus m. Okay. So, what I see is the following. I see that this is also equal to the summation m from 0 to infinity g of m, and let us now break down this factor z to the power minus r as minus r plus m as z to the power minus m summation r from minus m to infinity f of r z to the power minus r. Okay. So, then let me further assume that my function f of r is 0 for r negative. Why? So, this assumption makes sense if we are going to only work in with respect to the definition of Z transform. In bilateral Z transform this may not work. So, this assumption is completely valid when we are evaluating the Z transform. So, then this new sum, can be rescaled and summed from r 0 to infinity f of r z to the power minus r. So, I see that this thing is nothing but the Z transform of G, and this particular summation is the Z transform of f. So, hence I have shown that the Z transform of the convolution is the product of the Z transform. Okay. So, then let me give the more general result. So, more generally I have that the Z transform, the convolution is the summation m from minus infinity to infinity f of n minus m g of m. Okay. So, where my function f of n and g of n is 0 for n less than 0. So, if I describe my, so if I extend my definition of the function such that they are 0 for negative values of the argument, then I can extend my convolution in the negative half of the summation, okay, as follows. So, then if I were to prove, it can be shown that in this case the Z transform of the convolution is the product of the Z transform. Okay. So, I can this result can always be shown by using my bilateral Z transform. Okay. Okay. So, then let me highlight one more result, that namely the Z transform of the product of two function. So far I have shown you the Z transform of the convolution. So, my next result is the Z transform of the product of two functions, and that is given by this particular. So, I am just going to give you the result. This is given by this particular contour integral given by f of omega times g of z by omega d omega by omega. So, these are the respective Z transforms. Okay. So, these are the respective Z transforms to arrive to this expression. So, where I just want to highlight my C is a closed contour, it is a closed contour in the common domain of convergence, of f of z and g of z. Finally, in today's lecture I am going to highlight one more result, and that result is again described in the form of a theorem. This is the Parseval's theorem. The Parseval's theorem states that if I am given Z transform of two functions, let me just highlight that this is the Z transform of f, and I am given the Z transform of G to be capital G, then the Parseval's theorem states that the summation f of n times the conjugate of g of n from negative infinity to infinity is given by this, again this complex, this integral 1 by 2 pi integral from negative pi to pi f of e to the power I theta times g of e to the power I theta d theta. Okay. So, in particular, let me highlight the particular case of this Parseval's theorem. So, if my g is identically equal to f, so in that case I am going to get the left hand side is nothing but the summation of f, the absolute value of f square. So, this is also equal to 1 by 2 pi integral from minus pi to pi mod f of e to the power I theta. Well, so the original result was with a conjugate. Okay. So, f of I theta and then f conjugate I theta. So, I get an absolute value square d theta. So, what it tells me is that the spectrum of the function in the physical domain, the square of the spectrum will be the square of the spectrum of the function in the transform domain. So, with this I am going to conclude my today's lecture. In the next lecture I am going to highlight more results in Z transform, and specifically I am going to talk about some applications of Z transforms in solving some boundary value problems. So, thank you very much.